Purification of water on a large scale, like for water supplies for cities or for large gatherings. The water purification should yield safe and wholesome water, which has been defined as free water which is free from pathogenic agents, from harmful chemical agents, is pleasant to taste, that is, water is free from color or odor, and usable for domestic purposes like for washing clothes, for cooking. If the above criteria are not fulfilled, the water is said to be polluted or contaminated, that is, it is not potable water. Complete healthcare of the community is not possible without ample and safe drinking water. Water purification at a large scale. The steps involved in a typical water purification system comprise one or more of the following measures. Storage of water. Second step, filtration of water. And third step is disinfection of water. The actual steps would depend upon the source of raw water and the desired standards of water quality, that is, whether it is required for drinking or not. For example, groundwaters like spring water, deep well water may need only disinfection before consumption. On the other hand, surface water like river water, pond water tend to be turbid and heavily polluted and requires extensive treatment. Mostly for a large scale, we require all the three steps. First step is storage. Water is drawn from the source and stored in a reservoir, which can be natural or artificial. Storage helps in two ways. Provides a reserve of water from which further pollution is excluded, and considerable amount of purification occurs as a result of storing only. This purification is a natural process and occurs in all the three aspects, that is, physical, chemical and biological. Physical quality improvement occurs as by storing 90% of the suspended impurities. They settle down in 24 hours due to gravity. Water becomes physically clearer due to this, and this enables greater penetration of light, which further improves water quality. The chemical betterment is due to certain chemical changes which occur during storage, and these are oxidation of the organic matter present in the water by the aerobic bacteria using the dissolved oxygen. And this results in reduction of free ammonia and rise in nitrates. Biological changes are one of the greatest benefits of storage. A huge drop in the bacterial count occurs. The pathogenic organisms gradually die out, and it has been seen that when river water is stored, a total bacterial count drops by as much as 90% in 5 to 7 days. The optimum period of storage of river water is 10 to 14 days, and if the water is stored for longer periods, algae might grow, and this imparts a bad smell and color to the water. The second step is filtration of the stored water. In this stage, by filtration, 98 to 99% of the remaining bacteria also get removed. Other impurities are removed too, and one of the two types of filters may be used, biological or the slow sand filter, if the water requirement is not that high and a slow filtration rate can suffice, or mechanical or rapid sand filter. These have a higher rate of filtration and are required if the water requirement is huge and requires rapid treatment of water. Slow sand filter is one of the standard methods of water purification. Elements of a slow sand filter are: topmost layer is of supernatant or raw water. Below it is a bed of graded sand which is supported on gravel. Under drainage system, and finally a system of filter control valves. Slow sand filter, also called as biological filter. We will discuss in the next slides why is it known as biological filter. The topmost part of a slow sand filter consists of supernatant water, the depth of which varies, is kept between 1 to 1.5 meters, and this supernatant water serves two important purposes: provides a constant head of water, which overcomes the resistance of the filter bed and promotes downward movement of water through the sand bed. It also provides a waiting period, 3 to 12 hours depending upon the filtration velocity. And during this waiting period, the water is stored and undergoes partial purification as discussed previously by sedimentation, oxidation and particle agglomeration. The level of the supernatant water is kept constant. The next layer below the supernatant water is the sand bed. This is the most important part of the filter. The thickness is around 1 meter. The sand grains are carefully chosen to be of round shape and a small diameter of 0.2 to 0.3 millimeter. The sand should be free of clay and organic matter. The sand bed is supported by a layer of graded gravel, which is 30 to 40 centimeter deep, and this layer of graded gravel gives support to the sand above and prevents the sand from collapsing and being washed into the drainage pipes. The purpose of the sand bed is to provide a vast surface area for water to be exposed. The water percolates through the sand bed very slowly. It takes more than 2 hours. And during this slow percolation, purification of the water occurs through mechanical straining, sedimentation, adsorption, oxidation and bacterial action. The rate of filtration is adjusted so as to lie between 0.1 to 0.4 ml per hour, that is slow filtration, to enable the above mechanisms to take place and purify water. The vital layer of the slow sand filter, the heart of the slow sand filter, because of which it is known as biological filter, which is not there in the rapid sand filter. The vital layer of the slow sand filter lies within the sand bed. When the filter is newly laid, it acts merely as a mechanical strainer and it is not strictly biological at this time. But soon the surface of the sand bed gets covered with a slimy growth known as Schmutz deck. This is a Zuglier layer or the biological layer. It is a living layer and hence known as the vital layer. This is slimy and gelatinous and consists of thread-like algae, plankton, diatoms and bacteria. When this layer gets formed, this is known as that the ripening of the filter has occurred. The layer may take several days to fully form, and once it is fully formed, it extends 2 to 3 centimeters into the top portion of the sand bed. This vital layer is the heart of the slow sand filter. The vital layer removes organic matter, it adsorbs it, that is, holds back bacteria and oxidizes ammonical nitrogen into nitrates and therefore helps in yielding bacteria-free water. Therefore, until the vital layer is fully formed, the first few days filtrate is usually run to waste. The third layer of slow sand filter is the under drainage system, which is at the bottom of the filter bed and consists of porous or perforated pipes. The perforations are on the sides and not on the top because to prevent the sand from flowing into the water, into the pipes. These pipes serve the following purposes. One is to collect the filtered water through the perforations and provide an outlet for the filtered water. Also supports the filter medium above, that is form a network over which the gravel and sand are supported. Filter box encloses all the three elements. It is an open and rectangular box which is 2.5 to 4 meter deep, built wholly or partially below the ground, and the walls may be built of stone, brick or cement. Hence, it contains from top to bottom the following layers: supernatant water, sand bed and gravel support, filter bottom. Filter control are outside the filter box and constituted by some valves and devices which are incorporated into the outlet pipe system. The purpose of filter control is to maintain a constant rate of filtration. An important component of filter control is the venturi meter, which measures the bed resistance or loss of head of water, because of which filtration occurs. And when resistance builds up, the operator opens the regulating valve so to ensure a steady rate of filtration. When the loss of head exceeds 1.3 meter, it is uneconomical to run the filter because too less water is being filtered. Cleaning of the slow sand filter has to be done after the loss of head reaches 1.3 meters. Filter cleaning is done after the loss of resistance, which may occur after weeks or months without cleaning. When the bed resistance reaches to an extent that the regulating valve has to be kept fully open all the time, this is the time to clean the filter bed. At this stage, the supernatant water is drained off and the sand bed is scraped off. The top portion 1 to 2 centimeters is scraped off, which can be done by unskilled laborers using hand tools or by using the mechanical equipment. After several years of operation, 20 to 30 scrapings would have occurred. The thickness of the sand bed reduces to 0.5 to 0.8 meters, and this is the time to close down the plant and construct a new one. Advantages and disadvantages of slow sand filter. Why would you like to use a slow rate of filtration? It is simple to construct within one filter box. The cost of construction is cheaper than that of rapid sand filters. It does not need any chemical coagulation of water prior to filtering, which is unlike the rapid sand filters. Only water storing sedimentation is sufficient. It does not need highly skilled operators, and the physical, chemical and bacteriological quality of the filtered water is very high. Slow sand filters have been shown to reduce total bacterial counts by 99.99% and E. coli count by 99.9%. The disadvantages of slow sand filter are that it occupies a large area and the slow rate of filtration. It needs regular scraping of the sand bed for cleaning, and therefore in recent years people mistakenly consider that biological or slow sand filters are old-fashioned. The second type of filter is the rapid sand filter, which is a mechanical filter. These function in two ways. Gravity type uses gravity for filtration and pressure type uses pressure for filtration. The steps in purification of water using rapid sand filter is coagulation of the raw water, rapid mixing of the water and coagulant mixture, flocculation of the mixture, sedimentation, and then filtration using rapid sand filter. Coagulation. Raw water is first treated with a chemical coagulant such as alum. The dose of the alum varies depending upon the turbidity, color, temperature and pH of the raw water. The second step after addition of coagulation is rapid mixing to ensure thorough mixing of alum and water. The treated water is subjected to violent agitation in a mixing chamber for a few minutes. This allows a quick and thorough dissemination of alum throughout the bulk of water. This thorough mixing is very necessary. Flocculation. After rapid mixing, a slow and gentle stirring of the treated water is done in flocculation chamber for around 30 minutes. The flocculation chamber consists of a number of paddles which slowly rotate at the rate of 2 to 4 rotations per minute. These rotate with the help of motors. This slow and gentle stirring results in formation of thick, copious, white flocculent precipitate of aluminium hydroxide. The thicker the precipitate diameter, the greater the settling velocity. Sedimentation is the final step before the water can be administered into rapid send filter. The coagulated water is now led into sedimentation tanks where it is drained for long periods varying between 2 to 6 hours. Here the flocculent precipitates and takes along with impurities and bacteria. All these settle down in the tank, at the bottom of the tank. At least 95% of the flocculent should precipitate before the water is admitted into rapid send filters. The sludge which settles at the bottom is removed from time to time without disturbing the operation of the tank. The tanks should be cleaned regularly, otherwise they become a breeding ground for mollusks and sponges. Final step is filtration. The water which is partly clarified by the previous 4 steps is now subjected to rapid send filtration. Rapid send filter beds. Here again sand is the filtering medium. The size of the sand grain is larger, 0.4 to 0.7 mm in diameter. Each unit of filter has a large surface area. Depth of the sand bed is 1 meter. Below the sand bed is a layer of graded gravel 30 to 40 cm deep, similar to the slow sand filter. The gravel supports the sand bed and permits the filter water to move freely towards the under drains. The depth of the water on the top of the sand is 1 to 1.5 meters, similar to the slow sand filter. The under drains at the bottom of the filter beds collect the filtered water, again like the slow sand filter, but the rate of filtration is much higher, 5 to 15 liter per square meter per hour. But the rapid sand filter require frequent cleaning, because as the filtration proceeds, some alum floc which was not removed by sedimentation is held back on the sand bed. This forms a slimy layer which absorbs the bacteria and further purifies the water. Oxidation of ammonia occurs while the water is passing through the filters, but as the filtration proceeds, the suspended impurities and bacteria clog the filters, and the filters soon become dirty and begin to lose their efficiency. When the loss of head approaches 7 to 8 feet, filtration has to be stopped and the filters are subjected to washing process, which is known as backwashing. Backwashing is maybe required daily or weekly depending upon the amount of water and the loss of head. Washing is accomplished by reversing the flow of water through the sand bed. Backwashing dislodges the impurities and cleans up the sand bed. The washing is stopped when clear sand is visible and the wash water is sufficiently clear. The whole process takes around 15 minutes. The backwashing is completed in 15 minutes. In some rapid sand filters, compressed air is also used as a part of backwashing process. So the components of slow sand filter and rapid sand filter are similar except for the trough on top of the filter which carry the backwash water. Advantages of rapid sand filter. Rapid sand filter can deal directly with raw water. That is, no preliminary storage is required. Water is drawn and directly treated with alum, rapid mixing, flocculation, sedimentation and then filtration. So water need not be stored for partial purification. These filter beds occupy less space and filtration is rapid, 40 to 50 times faster filtration than slow sand filters. The washing of the filter is easier and therefore there is a more flexibility in operation. The disadvantages can be simply guessed that the operation requires qualified operators and that frequent washing is required and the water quality is a little inferior to that produced by slow sand filter. The final step before distributing the water supply is disinfection. So the final step in water purification is disinfection of the filtered water. The most practical disinfection at a large scale is chemical disinfection. A chemical can be considered suitable for use as a disinfectant in large water supplies if it satisfies the following criteria. The chemical should be able to destroy the pathogenic organisms present in the water within the contact time available, and this capability should not be affected by the range of physical and chemical properties of the water. The chemical should not leave products of reaction which render the water toxic or impart any kind of color or make it unpotable in any other way, like altering the taste too much. The chemical should be easily available and at a reasonable cost so that we can continue disinfecting the water supplies. The chemical should possess the property of leaving some residual concentration to deal with the possibility of subsequent recontamination during distribution or storage. The chemical should be detectable in water by practical and simple techniques, even in small concentrations, so that we can regulate the efficiency of our disinfection. We can check if the chemical is present in sufficient amounts or not, if it is too less or too much, and accordingly regulate our chemical disinfection. So it should be detectable by simple techniques. Chlorine satisfies most of the above criteria and hence it is widely used. Disinfection by chlorination. Chlorination is a supplement and not a substitute to sand filtration. Chlorine kills pathogenic bacteria but has no effect on spores and certain viruses like polio and viral hepatitis viruses except in high doses. In addition to being germicidal, it has other properties. It oxidizes iron, manganese and hydrogen sulfide. It destroys some taste and odor producing constituents. It controls algae and other slime organisms. When chlorine is added to water, it forms hydrochloric acid and hypochlorous acid. Hydrochloric acid only neutralizes the alkalinity of water. The hypochlorous acid ionizes to form hydrogen ions and hypochlorite ions. The disinfecting action of chlorine is basically due to hypochlorous acid and to some extent due to hypochlorite ions. Chlorine disinfects best when the pH of water is around 7. And when the pH value exceeds 8.5, it is unreliable as a disinfectant because 90% of the hypochlorous acid gets ionized to hypochlorite ions. But fortunately, most waters have a pH value between 6 to 7.5. Principles of chlorination. For adequate chlorination, following rules should be followed. The water to be chlorinated should be clear and free from turbidity because turbidity impedes efficient chlorination. The chlorine demand of the water should be estimated first. What is chlorine demand? The chlorine demand of water is the difference between the amount of chlorine added to the water sample and the amount of residual chlorine remaining at the end of a specified period of contact, which is usually 60 minutes, at the given temperature and pH of water. In other words, chlorine demand of the water is the amount of chlorine that is needed to destroy the bacteria and oxidize all the organic matter and ammonical substances present in water. The point at which the chlorine demand of water is met is called the break point. If further chlorine is added beyond this point, free chlorine begins to appear in water. Third is the contact period. A minimum contact period, that is presence of free residual chlorine for a contact period of at least 1 hour, is essential to kill bacteria and viruses. Only after that water can be supplied. It is said again that chlorine has no effect on spores and protozoal cysts and helminthic ova except when applied in higher doses. Once the chlorine demand of the minimum recommended concentration of free water and the residual chlorine is 0.5 milligram per liter for 1 to be applied is calculated. The free residual chlorine provides a margin of safety against subsequent microbial contamination such as may occur during storage and distribution. Chlorine gas is the first choice because it is economical. So the sum of the chlorine demand of the specific water plus the free residual chlorine of 0.5 mg per liter constitutes the correct dose of chlorine to be applied. A special equipment is known as chlorination equipment is required and the dosage of chlorine gas to water to be applied is calculated. In some water treatment plants, can be applied is used instead of chlorine gas. What is chloramine gas? Chloramines are loose compounds of chlorine and ammonia. Chlorine gas produce less chlorinous taste and give more persistent type of residual chlorine. But their greatest drawback is that they have a slower action than chlorine gas. Perchlorone or high test hypochlorite is a calcium compound which has 60 to 70% of chlorine, which is released when added to water. Solutions are prepared from HTH and then these can be applied to water for water disinfection. But as discussed already, chlorine gas has replaced all other chlorine derivatives in disinfection of urban water supplies. Disinfecting heavily polluted water. Superchlorination. Superchlorination followed by dechlorination. It is the addition of large doses of chlorine to the water and then removal of excess of chlorine after disinfection, after the contact period. This method is applicable to heavily polluted water whose quality fluctuates greatly. Breakpoint chlorination. What is breakpoint chlorination? It achieves the same results as superchlorination for heavily polluted water, but in a rational manner, and therefore can be called as controlled superchlorination. The addition of chlorine reacts with ammonia of water. Ammonia is due to nitrogen of organic matter in the water. The addition of chlorine reacts with ammonia in water and produces chloramines. These chloramines do not have the same efficiency as free chlorine, but are misread as residual chlorine. So when the chlorine dose in the water is increased, a reduction in residual chlorine occurs instead of increasing. And this reduction is because of the destruction of chloramines by the added Cl2. As the chloramines are read as residual chlorine and they are being destroyed, so there is a reduction in residual chlorine. The end products of chloramines are not read as residual chlorine. So this fall in residual chlorine will continue with further increase in chlorine gas dosage. But after a stage, the residual chlorine begins to increase directly in proportion to the added dosage of chlorine. This point where the residual chlorine starts to appear, when all the combined chlorines or chloramines have been completely destroyed, is called the break point, and the corresponding dosage of chlorine is the break point dosage. Hence, clean water will not show any break point. That is, the residual chlorine will rise with increasing doses of chlorine since the beginning. As discussed previously, we need to measure the amount of chlorine in waters to see if there is sufficient free residual chlorine is there or not. But free chlorine combines with ammonia and nitrogen of the organic matter present in the water to form chloramines. These chloramines are not as efficient residual disinfectant, yet these get included in the total residual chlorine content of the water when it is measured. And we intend to measure only the free residual chlorine because it is this only which will provide protection from subsequent contamination. So what we can do? We can measure free chlorine using orthotoletin test. The 10 seconds reading will be the free chlorine. And the total chlorine would be measured if we take the 5 minutes reading. So we can calculate the combined chlorine by subtracting free chlorine from total chlorines. What is OT test or orthotoletin test? It enables measurement of free and combined chlorine with speed and accuracy. The reagent used is analytical grade orthotoletin dissolved in 10% solution of hydrochloric acid. When this reagent is added to water containing chlorine, the water turns yellow and the intensity of the yellow color is proportional to the concentration of the chlorine. The yellow color is produced both by free chlorine residual and by combined chlorine, that is chloramines. So the test is done by adding 0.1 ml of the reagent to 1 ml of water. Yellow color that is produced is matched against charts within 10 seconds. This gives the amount of free chlorine. The yellow color appearing after a few minutes gives the amount of total chlorine. The orthotoletin test, however, is not accurate because some other impurities like iron, manganese, nitrate are likely to cause a false yellow color, indicating wrong and increased residual chlorine levels. So we have an improvement on orthotolidine test. This is orthotolidine arsenate or OTA test. This is an improvement of the OT test. It also determines the free and combined chlorines. In addition, the yellow color caused by presence of other interfering substances like nitrites, iron, and manganese are noted after dechlorinating the water sample. So the error is overcome. Recently, it has been discovered that chlorination of water can lead to halogenated compounds. Some of these are either known or suspected carcinogens. This has led to search for alternatives to chlorine, and some of these are bromine, bromine chloride, iodine, and chlorine dioxide. But till now, these do not seem to present a viable alternative to chlorine. Ozone is showing the greatest promise, but only as a complementary with chlorine. Similarly, ultraviolet radiation is a potent disinfectant, but only in combination with chlorine. Ozonation. Ozone is a powerful oxidant and it can be used as primary disinfectant. Ozone gas is first formed by passing dry air through a high voltage electric field. The resultant gas is ozone enriched. This is dosed directly into the water by means of porous diffusers at the base of the tanks. The contactor tanks provide 10 to 20 minutes of contact time. Dissolution of 80% of the ozone in the air is possible, and the remainder ozone is let off in the off gas. This off gas is first passed through an ozone destructor and then vented out to the atmosphere, because addition of ozone to atmosphere is actually polluting the atmosphere. The performance of ozonation relies on achieving desired concentration after a contact period. A residual of 0.5 mg per liter after a contact period of 20 minutes is typically used. The doses required to achieve this varies with the type of water. Higher doses are needed for untreated water because of higher ozone demand, because of natural organics present in background in natural waters. Ozone reacts with natural organics to increase their biodegradability. The biodegradability is measured as assimilable organic carbon. Ozonation is normally used with subsequent chlorination. Either pre-treatment with filtration and then ozonation, or subsequent activation with granular activated carbon followed by chlorination, because it provides chlorine residual, because ozone does not provide residual disinfection. Ozone is effective for degradation of a wide range of pesticides and other organic chemicals if that is a concern. Membrane processes. Membrane processes have been used for production of pure water for industrial and pharmaceutical applications, and are now being tried for treatment of drinking water even at a large scale. But these membrane processes purify water but do not provide residual disinfection. Hence, there is a need to add small amounts of persistent disinfectant like chlorine, which will act as a preservative during storage and distribution. The pore size of the membrane used in membrane processes is the smallest in reverse osmosis, and the pore size increases in the following order: reverse osmosis, nanofilter, ultrafilter, and the largest pore size is in microfilter. The membrane processes of most significance in water treatment are high pressure processes, reverse osmosis, and nanofiltration. These have the smallest pores and hence require higher pressure for the movement of solvent. And low pressure processes, ultrafiltration and microfiltration, as they have larger pore size, they require lower pressures to operate. Reverse osmosis. Principle of reverse osmosis. If two solutions are separated by a semi-permeable membrane, A semi-permeable membrane is a membrane that allows the passage of solvent but not that of the solute. In this condition, the solvent will naturally pass from the lower concentration solution to the higher concentration solution. This process is natural and is known as osmosis. It is possible, however, to force the flow of solvent in the opposite direction, that is from the higher concentration solution to lower concentration solution, by increasing the pressure on the higher concentration solution. The required pressure for causing this is known as osmotic pressure, and the process is known as reverse osmosis. It is equal to the osmotic pressure. Therefore, reverse osmosis creates two streams of water, one of treated water and another of wastewater, which is highly concentrated. Reverse osmosis rejects even monovalent ions and obviously organic molecules with high molecular weight. The most common application of reverse osmosis is desalination of seawater for provision of drinking water drawn from seawater. Nanofiltration uses a membrane with properties in between RO and ultrafiltration, that is a little larger pores. It allows monovalent ions like sodium and potassium to pass through, but holds back divalent ions like calcium and magnesium and higher molecular weight organic molecules. Nanofiltration may be effective for removal of color forming organic compounds. Then lower pressure membrane processes. Ultrafiltration. It has large pores, so can operate at low pressure. The principle is similar to RO, but the membranes have much larger pores and hence they can operate at lower pressure. Ultrafiltration membranes reject organic molecules. Microfiltration has still larger pores and operates at a lower pressure. And it can be said that is a direct extension of the conventional filtration into sub-micrometer range. That is the filters that are used in for domestic purposes. It's a little smaller pores than that. So it sieves out particles which are more than 0.05 micrometers. Hence the membranes reject only the colloidal and suspended material but do not block molecules. This microfiltration has been used for water treatment on large scale, but only in conjunction with, like after coagulation of water to remove particulate and some dissolved organic carbon, and then subjecting to microfiltration, and sometimes prior to reverse osmosis, so that the permeate flux in reverse osmosis is better because it has already been treated with microfiltration.